In this video we're going to recap the integrating factor method, which we've seen lots of times during lectures. And remember, that's this method that's used for solving first order linear ordinary differential equations. So remember, first order means that the highest order derivative is 1, so we've just got dy by dx, we haven't got any second derivatives here. And then linear is that property that says that for first order differential equations at least, the coefficient in front of dy by dx is some function of x, so in this case it's just the number 1, that's a function of x. The coefficient in front of the y term should also be a function only of the independent variable x, so it's p of x here, and the right hand side has to be also a function of x. So there's no y in these functions p and q here, they're just functions of the independent variable x, and that's what makes this a linear differential equation. So the way to solve these is first of all to identify that the differential equation itself is linear, and then to rearrange it into this form that we've got above, so get the coefficient of dy by dx to be equal to 1, rearrange it so that everything involving y is on the left hand side and everything that isn't is on the right hand side. And then the key step really is to multiply both sides by an integrating factor that we'll call r of x. Now, if we've chosen r of x in a smart way, and we'll say how to do that in a moment, then the left hand side will be the derivative with respect to x of the integrating factor multiplied by y. So the left hand side will be a perfect derivative, and so at that stage we can just integrate both sides of the equation with respect to the independent variable. In this example that's what we're calling x, so we'd integrate with respect to x and then we'd rearrange to get the final answer. Okay, so let's run through that procedure in a little more detail. First of all for the general case, and then we'll move on and look at an actual example with some specific functions p and q. So here we have the first order linear ordinary differential equation, and we said that we were going to multiply it by an integrating factor. And the way that we always choose the integrating factor, and we've derived y in lectures, is to say that r of x, the integrating factor, is e to the integral of p of x dx. Okay, where p of x is this function here, it's whatever is multiplying y, the dependent variable y. Okay. Really the reason why we choose this is because if you then look at what dr by dx is, the derivative of r with respect to x, then it will be p of x multiplied by e to the integral of p of x dx. So that's just differentiation. And e to the integral of p of x dx is just r of x. So in other words, dr by dx is p of x times r of x. Okay, so why is that useful? Well, if we multiply throughout by r of x now, then we get this expression here, so the yellow expression. Now let's focus our attention on the left hand side of this yellow expression. So this first term is r times the derivative of y with respect to x, but then this second term, r of x, p of x times y, well, this r of x times p of x is something we've already seen, because we said that that was what dr by dx was up here, because dr by dx was equal to p of x times r of x. So this left hand side is r times the derivative of y with respect to x, plus y times the derivative of r with respect to x. And that sounds like what you get when you use the product rule of differentiation. So it means that we can rewrite this left hand side as the derivative with respect to x of r of x times y. So again, just to explain why that is, if you think about doing it the other way around, so in other words starting from the bottom and working your way up, if I asked you to differentiate r times y with respect to x, given that both of those are functions of x, then hopefully you'd use the product rule. So you'd say okay, that derivative will be r of x times dy by dx, which is this first term, plus the derivative of r times y. And the derivative of r, as we said over here, was dr by dx is equal to p of x, r of x. Okay, so you can see, kind of unwrapping this with the product rule, that this left-hand side is this derivative. And then it just becomes a problem of direct integration. So you can integrate both sides of that with respect to x. On the left-hand side, that's going to undo this derivative, so we're going to have r of x times y. On the right-hand side, we're going to integrate r times q with respect to x, and we're not going to forget that arbitrary constant, so let's call that a. So that's just the constant of integration. And then finally, to get the explicit particular solution, all we have to do is divide both sides by r. So we have that y is 1 over r of x times all of this stuff up here. So that's how to do it in the general case. Now let's move on to look at a specific example with some actual functions instead of this general p and q. So in this specific example that we're going to look at, we're asked to solve dy by dx minus 2 over x times y equals 5x squared cos 2x. And we've got a boundary condition as well that says that when x is equal to pi, then y should be equal to 1. Okay, so we're not actually told here to use integrating factor, so we should just check that integrating factor is a sensible thing to use. And in order to check that that's sensible, we should check that this is first order and linear. Well, is it first order? Absolutely, because we've only got this derivative here, dy by dx. It's the first derivative, so yep, it's first order. It's first degree because that derivative is only raised to the power 1. In other words, it's not squared or cubed or anything. And then the coefficient of the y term, the term in the dependent variable, is a function only of x, the independent variable. And then the right-hand side, again, doesn't depend on y. So yeah, this is a linear first-order ordinary differential equation. Therefore, it's going to be sensible to try using the integrating factor method in order to solve it. So let's give that a go. The solution would start by saying, right, let's note that the ODE is linear in first order, as we've just said. Therefore, we're going to multiply both sides by an integrating factor, r of x, and now we have to figure out what that integrating factor is. So we said that it was always e to the integral of p of x dx. And p of x is whatever the coefficient of the y term was once we'd rearranged it into this particular form. So this is going to be our function p of x. It's going to be minus 2 over x. So the integrating factor is e to the power of the integral of p of x. So the integral in this case of minus 2 over x with respect to x. So we need to figure out what this integral is and then what e to the power of this integral is. So first of all, let's see if we can figure out what this integral is. Well, it's e to the minus 2 lots of the integral of 1 over x dx. Okay. And then what is the integral of 1 over x dx? Well, that's just the logarithm of x. So this is e to the minus 2 log x. Okay, you might think, well, don't we need an arbitrary constant? In this case we don't, because we're going to multiply both sides of the differential equation by r of x. If we did add an arbitrary constant in, we'd end up multiplying both sides and it would cancel. So when you're working out what the integrating factor is, you actually don't need to worry about the arbitrary constant. Now, can we simplify this, e to the minus 2 log x? Well, yes we can, because we can say that this is e to the log x all to the power minus 2. So this is just using the laws of exponents. And then e to the log x is nothing more than x. So x to the minus 2 is going to be our integrating factor. R of x is equal to x to the minus 2, or in other words, 1 over x squared. So our next step is going to be to multiply both sides of the differential equation by 1 over x squared. So if we do that, then we end up with this simplification here. So what have we done here? We've taken the original equation, we've multiplied both sides of it by 1 over x squared. It's a very common mistake to make to forget to multiply the right hand side by the integrating factor as well. So remember, multiply everything by the integrating factor, in this case 1 over x squared. If we do that, then we get some simplification. So for instance, in this term here, we've got x squared times x on the bottom, that becomes x cubed, and these x squares here are going to cancel because one's in the numerator, one's in the denominator. So we end up with this expression here, and then because we've chosen the integrating factor in that way, this left-hand side is now a perfect derivative. It's a derivative with respect to x of y multiplied by the integrating factor. So the integrating factor was 1 over x squared, so it's the derivative of y over x squared. Just as it was in the general case, it's probably easier to see that that's true by considering things in the kind of backwards direction. So in other words, to unwrap this derivative using the product rule. So if we ask ourselves what is the derivative with respect to x of 1 over x squared times y, in other words x to the minus 2 times y, then we do that using the product rule because y is a function of x, x to the minus 2 is also a function of x, so this is the product of two functions of x. And if we wanted to work out what that derivative was with the product rule, then we'd have x to the minus 2 times the derivative of y, so dy by dx. And then we'd add on the derivative of x to the minus 2 with respect to x, which is minus 2x to the minus 3 multiplied by y. Okay, and if we look at what we've got here, this is exactly the same as the left-hand side that we had up here, because we had 1 over x squared dy by dx, well that's just the same as x to the minus 2 dy by dx. Then we had minus 2 over x cubed y, well minus 2 over x cubed y, minus 2 over x cubed y. So these are exactly equivalent, these two last yellow lines. Okay, so now the left-hand side is the derivative of something with respect to x, so we can just integrate that directly with respect to x, and so we have to do that with the right-hand side as well. So with the left-hand side we're going to have y over x squared, and on the right-hand side we have to integrate 5 cos 2x with respect to x. So that's going to give us 5 over 2 sine 2x, and because we're doing some integration here, we mustn't forget our arbitrary constant. So we find that y over x squared is 5 over 2 sine 2x plus a. Now we can multiply both sides by x squared to get y on its own. That gives us that y is equal to 5 over 2 x squared sine 2x plus the arbitrary constant a times x squared. So now we've found the general solution, now we just have to apply the boundary condition to get our particular solution. Because remember, we had this boundary condition that when x is equal to pi, then y should be equal to 1. So here's our general solution that we've just found. Let's apply the boundary condition. So all we have to do to apply that is to say, well, we've got a condition for when x is equal to pi, so wherever we see an x, let's stick in pi. So we've got 5 over 2 pi squared sine 2 pi plus a pi squared, and the condition says that that must be equal to 1. Now, sine of 2 pi is just 0, so this first term is just 0. And then we're just left with a pi squared equals 1. Rearrange that by dividing throughout by pi squared. We get that a is equal to 1 over pi squared. And then we can put that back into the general solution. In other words, replace this a that we have up here with 1 over pi squared, and we get the particular solution. So this is the final answer. Y is equal to 5 over 2 x squared sine 2x plus 1 over pi squared times x squared, or x squared over pi squared. And that's the final answer.